Hello everyone and welcome back to ENL 582, Modeling and Control of Electric Machines and Drives. So we start the course now before jumping into talking about electric machines by recap on AC circuits. You will need this much throughout the course and especially for the first lap, so we need just to get this out of the way and refresh our memory a bit about talking about the AC circuits and quantities in single phase and in three phase, okay? So the well-known stuff here is just you have two kind of sources. The first one is the DC source, and that is a voltage source here. We draw it like a battery like this, and if it is applied to a load R here, and that is V, and the current will move here will be I, okay? If you try to plot this voltage with time like this, it will give you something like this, okay? That is constant in magnitude and also constant in polarity, okay? So the magnitude doesn't change with time, it's just constant like you see, and the polarity is constant. That means if it is positive, it's positive all the time. If it's negative, it will be negative all the time. That means this direction of current will remain constant like that, or just fixed, coming out from the positive terminal of the source and going back to its negative terminal, and that's why we call it constant polarity. But it's not the thing we want to talk about here. The thing we'll be dealing with all of the time is the AC circuits, okay? So now we have this AC voltage source, and that will be the impedance of the load, Z, okay? And that is the voltage V, and that is current I, okay? And I'm having those as small letters, not capital letters like the DC, because that is the notation we use with AC, just changing with time, okay? If you wanna draw it like this, that is a V with time. If it is a cosine wave, it will look like something like that, okay? That is the magnitude of the signal. Let's call it V hat, something like that. So as you see here, this V will equal to V hat, which is a magnitude, cosine omega t plus theta V, okay? So as you see, it's just a cosine wave like this. It may be a sine wave, it just depends, okay? So this V is the magnitude, okay? This omega equals to pi f, okay? Where f is the frequency in hertz, and the theta V is the phase shift, okay? So for this angle, the phase shift equals 0 because the maximum of the cosine started with 0 in time. But if it is shifted, this maximum of the cosine is shifted in time, then you will be having a phase shift value of theta V. Okay, guys? And you know the idea, it is just the frequency f equals 1 over t. T capital is the period of the signal, because that's a periodic signal. So you have a period that keeps repeating all over again. So if it starts with here, that will be your period from here to there, okay? So that is the period of the cosine wave t. If you have 1 over this value, will give you the frequency in hertz, and you want the angular frequency omega, which is 2 pi f, okay? So that is how you represent the AC circuits, and that is the idea. If you see now, that is basically changing in magnitude. Like you see, the magnitude keeps changing all the time, and also the polarity, it's something sometimes positive, sometimes it's negative. That means this current over here will keep changing in position. Sometimes it will be just going like this, and sometimes it will just change direction like that, because the voltage that's applied here doing the same thing will be sometime positive, sometime negative, and that is the AC signals we're using most of the time, because you know our public grid still now AC transmitted, so the electricity is generated in AC by the generators. We'll be talking a lot about synchronous generators and how they actually generate this AC electricity, and then they're being transmitted and distributed to the loads all like AC, like this. Okay, so if you wanna just keep investigating this and going sometime with, so this V representation here, I want to call it V of t, just to refresh your memory all the time. That is a function of time and changing in time like this. And this, we call it the instantaneous value. Okay, because that's changing every instant. So this is an instantaneous value. It's the representation versus time like that. Okay, it's more handy in the calculations, all that's to represent it in polar form. Okay, that means these AC signals, as you can see, yeah, it's changing in magnitude, but it's amplitude or magnitude. So this magnitude or amplitude, this amplitude or magnitude, that's V hat we're talking about, so will keep constant all the time. Okay, so you can really present it once you know its frequency. You can see V, which is capital V, with a dash over it, equals V and angle theta V. Okay, where this V is the RMS value of this and equals the magnitude V hat over square root of t. Okay, guys, and the theta V is the phase shift we talked about before. Yeah, so that's actually how you represent anything in AC. You need just the magnitude, V hat or VRMS, because they're just it. So if you know one of them, you can find the other one easily, the RMS and the magnitude or the amplitude. And if you know the phase shift, and by the time you know the frequency, because most of the time the frequency is the frequency of the public grid. So if it is here in North America, that's 60 hertz. In most of the other places in the world, it's 50 hertz. So you can know the frequency easily. So that's all the information you need to represent your signal. Actually, the magnitude and the phase shift and the frequency is known by definition where your place is. Okay, so that is the idea we're having here. Okay, if you want to represent the current going through the circuit here, so that is I of t also. Okay, so this I of t will be from Ohm's law here as V of t divided by the impedance Z, which this can be represented like the same thing, I magnitude cosine omega et plus theta I. Okay, guys, that is the same thing, but this phase shift angle will be changing depending on the load. Okay, and also it can be represented in the polar form like that. I will also equals I, but that's now the RMS. Keep that in mind with angle theta I. It will be the same thing like we talked about the voltage. Okay, so that's the voltage and the current. We're more concerned about the power that can be just transmitted to this load. So also the power will be a function of time, because you know that the power is just V times I. They're all small numbers over here, or small letters, sorry. So this V will be small like this, just to differentiate it, you know. Okay, guys. So if you just multiply those representation, which is V cosine omega et plus theta V, and multiply by the current, which is I magnitude cosine omega et plus theta I. Okay, and you have your function cosine, all that stuff. It will land out with V I cosine theta plus Vi cosine 2 omega t, plus theta. Okay, guys, So keep in mind, again, when saying just V like that, and I will talk about RMS values, not the magnitudes here. And this angle theta, this angle theta and this angle theta equals theta V minus theta I. Okay, so it's just a refresh your memory. You should be talked about this before so much in other things. So this theta is the phase shift between voltage and current, and that's the angle we're more concerned with all the time. Okay, by the way, in most cases we use the voltage angle theta V, this theta V, as the reference, so most of the time we put it with 0, and that means your theta I will be just basically equals minus theta. So theta equals theta V minus theta I. So if theta V equals 0, that means theta equals minus theta I. But that's just the way most of the time we just do this, but it's not mandatory, you know. So this power, if you look like this, so theta here, which is the phase shift, should be a fixed number, a constant number, doesn't change. And that means this P of t have two parts, okay? This part is a constant part, and this part is an alternating part because of cosine 2 omega t, but alternating in double the frequency of the voltage and the current. Because the voltage and the current is in terms of omega t. Sorry, I keep doing omega et, so just keep the notation. So that's omega, okay? But this power has two parts, so if you're trying to plot it like that, it will be having a fixed component, we call it a DC component, which is Vi cosine theta, and then the rest is just, okay guys? So that's alternating in double the frequency of the voltage and current, okay? So this fixed value, we call it the average value of the power, and that is the thing that we are more concerned with. So P average will equals Vi cosine theta, and this is measured in watts. Okay guys? So if you have an AC circuits, you need the RMS value of the voltage multiplied by the RMS value of the current cosine theta, and theta is the phase shift between the voltage and the current. Okay guys, so that is the P average, and keep in mind we call this the active power. Sometimes we call it the useful power, because that is the actual power that is being used, because that is the power that can be dissipated into resistors, so it can be used for heating loads and lighting loads, and that is also the power that can be converted from electrical to mechanical, and that is the thing we're more concerned with in this course. So this amount of power, that is the power that can be converted into mechanical energy, and that's why we call it active power or useful power. But why we say that? Because in AC circuits we just don't have this power alone, but we have other powers also. So these powers will begin by defining the apparent power, okay? Which is S. Okay? So that is a complex value, you call it all the time. So S, to calculate it, will be V as a polar form multiplied by I conjugate. Okay? This term is conjugate, and that is the negative of the angle. So if you want to calculate this from the polar form, it will be V RMS, you know, just V capital like that, mean the RMS value. I'll keep doing this with angle theta V multiplied by I RMS with angle theta I. But as this I is conjugate, that means you adding a negative sign to it. Okay, guys? And that means this equals V I with angle, that is the summation of those, theta V minus theta I. That is what we know by theta. So it's V I and angle theta. Okay, guys? So that is S in the polar form, or the complex form, which you can represent it like that. So S equals VI cosine theta plus J VI sine theta. If you remember, this VI cosine theta is actually the P, the useful power, the average power, P, okay? And this part, which is the complex part, J here, or the imaginary part, sorry, we call it Q, which is the reactive power. We measure this in VAR, volt ampere reactive. Well, this is measured in VA, which is in volt amperes. Okay, guys? So this is the three powers we have here. So this is S, which is the apparent power, which is the complex summation of the active power and the reactive power, because P is your active power measured in watts. Okay? So those are three different sorts of power in AC circuits. The apparent power, the S, which is the complex summation of the active power or the useful power, P, and the reactive power, which is Q, measured in volt ampere reactive. So S is basically can be just dealt with like the any other kind of complex numbers. So you can find it like that from the complex triangle. So this is P, and that is Q, and this the S, and apparently this is the angle theta, which is the phase shift between the voltage and current. Okay, guys? So from this triangle you can find all what you want. Okay, so basically if you want to find the magnitude of S, okay, it will be the square root of P square plus Q square. Yeah, and from the same thing you can find P simply if you have S from S cosine theta, and Q will be S magnitude sine theta. Okay, guys? And we need to mention that if you have this theta, which is a phase shift, the cosine of this theta from the triangle will be P divided by the magnitude of S. Okay, guys? And this is a very important value. We call it PF, the power factor. Okay? This value gives you this from the total power you have in the AC system, which is the apparent power, the S, how much of it is actually useful power. Because again, that is the power which can be transmitted into mechanical energy and other forms of energy that we need for our loads. Okay? So you are forced to have reactive power in the system because that's an AC and it's just having loads, which is not all the time resistive loads. So you'll be having reactive power in the system, but the thing you'll be looking at most of the time is the useful power or the active power, and that's why we use the power factor as an indicator of how much of our total power, which is S, is actually useful power. So if the power factor is 0.8, that means that 80%. So when you say that the power factor is 0.8, that means that 80% of the power here is active power or useful power that is ready to be converted from a form to another, from the electrical form into mechanical form or the, okay? So that was what we need to talk about the regular or just the AC circuits here, okay? And this AC circuits actually is single phase AC circuits because just that is the way it goes. Okay, so I need to jump here to talk about this. That's the most important thing I want to talk to you about today, which is the three phase circuits. Okay, guys, what is this? It is just, rather than just have 1 volt signal like this, so this circuits we've been talking about the V. So that is dead, and that is V, and that is the current I of t. Sorry, let me say it I. Okay, this is a single phase. Okay, that's the idea. Just because you have a single voltage source and a single load like this, and they're just having one current flowing from this source to the load. Yeah, it's not the idea of having just a single load. It can be multiple loads connected in series or in parallel. That's still considered just when lumped together, it will be an equivalent to one load, you know. So this is the single phase. The idea is the brilliance of having three-phase circuit is just what if we can multiply the amount of power that can be transmitted from the system by 3. Okay, if you want to have 3 times the power that can be goes from this load, from this source to the load. Okay, so if this, and that's actually how it works in the real life, it's this source is the generator, or the power plant that's generating power for you. And if this load is basically any loads you want, let's say domestic loads, it's our homes now. Okay, so if you want to transmit power from the power source here to the loads, you will need 2 lines for transmission. Okay, this we call the line, and this that the current is coming back from we call the neutral. Okay, so if you want to have 3 of this, you will need to have 3 identical circuits of the same thing. That means you need 6 lines like that. Okay, so it comes with the idea of what if we have this as 3-phase circuits, then we will be able to transmit 3 times the power, but not with 6 wires. It will be using 3 or 4 wires depending on the connection, and that is the idea we'll be talking about here. Okay, the 3-phase circuits. Okay, so how actually we use this with 3-phase? Okay, is we are using 3 signals. So a signal can be voltage, can be current, okay, equal in magnitude and have equal phase shift of 120 degrees, which equals 2 pi over 3 radians. Okay guys, how this can be, I can actually draw this, but because we want it to be look good, I'm sorry. I'm gonna have a better photo for you. Okay guys, so like you see here, you have 3 signals. Okay, this black one we call it phase 1, and the red phase 2, and this blue is phase 3. So those all have the same magnitude, like you see. So that is the magnitude of them, that's constant all the time. So sorry, the magnitude is constant between the 3 signals, and you will have the same phase difference between them. So the phase difference means look at any point in one of them. So yeah, so from this peak of the black one at 90 here to the peak of the red one, phase 2, this is 120 degrees, or 2 pi over 3. Okay, it will be also from the next ones, from the red to the blue, phase 2 to phase 3, that is 120 degree, or 2 pi over 3. Okay, this what we call a balanced 3-phase signals. Balanced means they have the same magnitude, okay, and fixed phase difference, which is 120 degrees from one signal to the next ones. Okay, and that is the kind we want all the time, okay? Because if they are not balanced, it's not giving us the same advantage we need, okay? So the idea is we use 3 signals like that rather than just 1 signal. So rather than just having 1 source like this voltage source, we will have 3 voltage sources, okay? Those voltage sources have the same magnitude and 120 degrees phase shift between one to the next one, okay? Will be the same with these loads. Z loads will be, rather than just have the load lumped as Z, it will be also connected in 3-phase. So everything in the system will be in the 3-phase, and that's actually what's happening in our public grid, is everything in 3-phase, okay? So the power generation happens in 3-phase. That means our synchronous generators, the machines that actually generating electricity, is built into 3-phase, and we'll be talking about this in much details when we're talking about synchronous machines. So they are generating actually 3-phase voltages like what you see in the photo here, okay? And it's transmitted like 3-phase and go to loads, which is also connected like in 3-phase most of the time, okay? Yeah, it can be like in single phase, like homes and something like that, but again, they are connected in different phases to keep it locked like 3-phase, okay? And we are trying in the public grid to distribute the loads, the single phase loads of our homes and all that stuff on these 3-phase lines as equal as we can to keep this balanced as much as we can, like we talked about here. So that's what you call about 3-phase system, okay? The math of this will be the same, okay? So we having 3 phases, I'll call them A, B, C, okay? So the VA of T will equal V magnitude cosine omega ET plus phase shift theta V, okay? VB of T will equal the same, V cosine omega ET plus theta V, but now minus 2 pi over 3. Okay, and VC of T, the third one, will be also V cosine omega ET plus theta V minus, or so take it plus here, 2 pi over 3, sorry. Okay, it should be actually, so this plus 2 pi over 3 equals minus 4 pi over 3. Okay, so we are doing the same idea we talked about here. So that is V magnitude, because all of this fundamental, this balance, that means the 3 of them have the same magnitude, okay? And of course they have the same omega E, which is the same frequency. Call it omega or omega E, whatever it is. Let me keep the same notation here. So I will call it omega, not omega E. So that is omega T, and omega T, okay? So they have the same frequency because they have the same omega, okay? And the initial phase shift, which is theta V of this angle, will be constant here, okay? And they have phase shift. The other ones, the second one, B, have minus 2 pi over 3. That means it has a 2 pi over 3 shift from the A phase. And then VC is also 2 pi over 3, which is also from C, it's 2 pi over 3, okay? So that is the idea we'll be talking about here, about just balanced 3-phase. That is the instantaneous form of them. If you want to go in polar form, so the VA equals V with angle theta V, okay? The VB equals V, the same magnitude, with angle theta V minus 2 pi over 3. And VC will equal V, the same magnitude, with angle theta V plus 2 pi over 3, okay? If this phase shift initial one equals 0, they will be like VAV with angle 0, and the other one, VB, will be with angle minus 2 pi over 3, and VC will be with angle V with angle 2 pi over 3. Okay, guys? The same thing with the currents that can move from the source. So IA will equal I, our mass, don't forget that, and angle theta I, and IB will be with angle theta I minus 2 pi over 3, and IC will be I, our mass, with angle theta I plus 2 pi over 3. Okay, guys? So the same thing here, we're talking about if you applied balanced three-phase voltages, that means they have the same magnitude and phase shift equals 120, 2 pi over 3. That will give you if those, so this is balanced voltage. Balanced three-phase voltage, actually. Okay, so balanced three-phase voltages applied to balanced three-phase load, and balanced three-phase load means that impedance of each phase are equal. That means the three phases have the same impedance, will give balanced three-phase currents. Okay, guys? So if you have balanced three-phase voltage, the same magnitude and fixed phase shift of 120 degrees applied to three-phase loads impedance will give you balanced three-phase currents. Okay, but how this can be applied or all that stuff? Okay, so we had the just main idea. It is just rather than just having one voltage source and one load, we will have three voltage sources and three loads. But how those actually can connect it together, because they are not separate, otherwise it will not be three-phase, it will be three separated single phases. Okay, so to have it like three-phase, you have to connect them. Okay, so that takes us to actually what is the three-phase connections. Okay, so they're very, very popular. You have two connections, the Y connection, sometimes we call it star connection, so it's Y connection or star connection, whatever you want, and the delta connection. Okay, so what about these connections, how they are, and how actually we can deal with them? Okay, so I'm gonna start here with the Y connection. So the idea that you have three voltage sources or three loads, whatever you want to deal about them. So how you connect them? You can connect them like Y connection. Okay, so here is the idea, is that is the first voltage source, VA. Okay, and I will connect it in star or Y connection like this. So that is VB, and that is VC. Okay, that's why we call it star connection. They're connected like that. Okay, and the same thing I will do here with the load. Okay, so that is Z star and Z star and Z star. Okay, so that is a Y connected source and a Y connected load. Okay, it's not mandatory to connect star load to a star source. You can connect a star load to a delta source or vice versa, but it's just here we are trying to make things simple just to look around. Okay, and you connect between them by this line from this here to this one. Okay, and from this one here to this, and from this one here this. Okay guys, I'll be calling these points here A, that is C, that is B, and here the same thing. Okay, but let's call this A dash and this C dash and this B dash. Okay guys, and this point, actually the connection between them, we call it N, the neutral point, like we said before. Okay, and this here will be connected also with the other neutral point on the other thing, call it N dash or something, and this will be just like that. I will have this like dash lines just to keep it in your mind all the time. That is the neutral line. Okay, so as I said here, there's 3 phases, and we connected to the other 3 phase loads with just 4 wires, like you see. Okay, if we have 3 separate single phases, each one of them will be having a line and a neutral, so there will be 6 wires, not 4 wires like that. Okay guys, so each one of those is a line. So this is line, this is line, this is line, and this is the neutral. Okay guys, and if you have this in mind, each one of those is a phase. You know that. So that is a phase, that is a phase, and that is a phase. The same thing with the loads. So that is phase and phase and phase. Okay, we call them, that's phase A, that is phase B, that is phase C, and also in the loads, that is phase A, that is phase B, and that is phase C. Okay guys, so if I wanna just have this here, okay, so with these connections we will have 2 different values for everything. Okay, so we'll have the phase quantities and the line to line. Let me write it again. Line to line quantities. This line to line, most of the time we call it just line quantities for the sake of simplicity. Okay, so what does it mean by phase quantities versus the line to line quantities? Okay, so it should be obvious. If I want you to find me the phase voltage of A, that means I want this value, the VA. Okay, but again, what I want to the phase voltage of B, that means I want this value, VB, and VC, the phase voltage of C. Okay, also I want the phase voltage of the load. That means I want this value, V phase A, because that is the voltage across the phase. Okay, so this phase quantities, we call it the phase to neutral values, because like you see, you just measuring across from a line to neutral. Okay, it will be the same thing with everything if you want. Okay, so that is a phase B, so that is V phase B, because that is no, that's C, I'm sorry, confused here. So because this point C, so that is the line C. Okay, so that is V phase C, and on the same thing, this will be V phase B, because that is a voltage between the line B and the neutral. Okay guys, and that's why I call this line A, because that's connected A to A dash, and that is line C, and that is line B. Okay, so that is the phase quantities. Okay, but what about the line to line quantities? Should be obvious. It is just these values, but from a line to line. What if I wanted to measure me the voltage between line A and line C? It would be something like this. Okay, so that is line voltage or line to line voltage. As I said, you call it line voltage or line to line voltage. Okay, but that is, we call this VAC. Okay, guys, by the same thing, that is from here to down, that is VAB, from line A to line B, and from those guys together is VBC. Okay, so that is the idea we'll be talking about here. Alright, so I can give me a phase quantity. That means it's from a line to neutral, from phase to a neutral. Okay, if I wanted to a line quantity, that comes from a line to a line. So this drawing should be kept in your mind all the time, because it will just give this in your mind easily. What is the line quantities and what is the phase quantity and all of that. Okay, guys? Okay, so how actually you can calculate this or differentiate this or have this in mind? Okay, so I'm gonna just take a small portion of this load here and redraw it down here. Okay, so this is the line A, okay, and that is the load. Okay, guys, it's the same thing here, yeah. Well, that is ZA, phase A, and that is ZB, and that is ZC. Okay, I'm gonna just have this down here, because that is A dash, and that is C dash, and that is B dash. Okay, so the voltage from here to there is VAN. Okay, because this is N. Okay, but the voltage between the A and B here is VAB. Okay, that is line voltage, but this is VN is phase voltage. Okay, guys, and this value of voltage from here to there is VBN. It's also a phase voltage from B to N. Okay, so they are all phase values, VAN, VBN, and here VCN. And you know that VN and magnitude equals VBN equals VCN, but they have a phase difference of 120 degrees, 2 pi over 3. Okay, but what if you want to calculate from this guy this line voltage, V line to line, or line as we said, which is VAB? Well, basically from this here, if you can see it, okay, just using Kirchhoff voltage law if you want. Okay, so there is VAN, meaning the positive here and the negative here, and that is VBN, that means the B, which is here, is positive and here is negative. Okay, guys, from this and using the Kirchhoff voltage law, VAP will equals VAN minus VBN. Okay, guys, this will be equal, so the line voltage here in the star connection or wire connection will be the difference between two consecutive phase voltages, which is VAN minus VBN like you see here, okay? But what about the current? So that is the line current, I line, because that is the current moving in the line. Yes, because we said this is the lines, yeah? But what about the phase current? That's the current moving into the phase. So this moving into the phase is I phase, okay? You will have another phase current coming here, another phase current coming here, another line current coming from here, and a third one coming to this one, okay? They are not equal each time, but you know those currents, if everything is balanced, will be equal in magnitude, and also 2 pi over 3 phase shift between each of them because they are balanced 3 phase, okay? In a Y connection like that, if you can see this I line, it's all going into the phase, and this give me this nice thing that I line will totally equal a phase for the Y connection, okay? So the line-to-line voltage is different from the phase voltages here because the line-to-line voltage is VAN minus VBN, okay? But the line current equals the phase current, as long as you're talking about a Y connection. Okay, guys? By the way, to keep this in mind, and I actually will end with this, is I neutral, because you know there is the neutral current that should be moving here, I neutral, IN, cause IN, if you can see it from here, is basically equals I phase A plus I phase B plus I phase C. Okay, guys? This from mathematical or from everything, if you just get the values for this IA, which is IA cosine omega ET, and IB, I cosine omega ET minus 2 pi over 3, and IC is I cosine omega ET plus 2 pi over 3, and just added them together, it will give you 0. Okay, so as long as it's balanced 3-phase system, this summation of the currents, of the phase currents IA, IB, IC, which is basically the neutral, because as you see, these currents is going into here, and this is going into here, and this current is going into here, so they are all our summations are just summed in this point to come back from the neutral, okay? So they are all going into here, and they are just summed together at this neutral point to come back like this here, okay? So I neutral is the summation of the 3 currents. If they are balanced, they will cancel out and the I neutral will be 0. So there is no current will be moving in the neutral. Okay? So as long as it is a balanced 3-phase system, the neutral current will be 0. Otherwise, it will have a different value. Okay? Okay. So as we said, the I line equals here the I phase, as long as you're talking about a Y connected one. Okay, but the V line to line, VLL or V line to line in the Y connection, which is equals here the difference between the 2 consecutive phases, which is VA minus VB, or VB minus VC, or VC minus VA. If you work out the mathematics of this, will be square root of 3 V angle theta phase plus 30. What I'm saying about here, that if you want to calculate the line to line, so the magnitude of it will be square root of 3 times the value of the phase current. Okay, so this is RMS, so that is square root of 3 times this V, and it will have phase shift with 30 degrees. Okay, so if you're talking about this, if you have the phase voltage, which is VAN, equals V and an angle theta phase, any angle, and you want the line-to-line voltage of this, you will be basically having V, and that is the V line-to-line. Let me say that is the first V line-to-line, which is VAB, will be equal square root of 3 V, and you have this angle, and you add 30 degrees to it. So that's pretty easy. If you have the value of the magnitude and the phase shift of the phase A, or any phase actually, you can directly calculate the line-to-line voltage like that. You don't need to go and just have VAN and VBN and just subtract them. It is the same math. If you applied it, you can find this easily from here. So for a Y connected circuit, the I line equals I phase, but the V line to line VAB will equal square root of 3 times V, which is the phase RMS voltage, and you will have a 30 degrees phase shift in angle between them. Okay, guys? So that's all I need to talk about the Y connected circuit. The next time we'll be continue this by explaining the delta connected systems and explore the differences between them. Thank you so much for listening to me today. I know it has been a lot of information taken around here, so take time to study this, look at it, and I will be happy to receive your questions as we arranged before in the online meeting. Okay, guys, thanks so much for listening and joining to me today, and see you next time.